Alright, time for a video on the basics of chemical reactions. I posted a video on balancing now, just some of the basic terminology and ideas that you have to know in relationships to chemical reactions and chemical equations. Start off with the equation themselves and the format of those equations. All of the chemical equations you see are going to follow the same exact format, with the reactants on the left side of the arrow, the products on the right side of the arrow. Reactants first, then products. Reactants are what we start the reaction with, the chemicals we have before our change takes place. The products are what we have after the change takes place. So if we have this equation here, H2 plus O2 producing H2O, the hydrogen and the oxygen are our reactants, the water is our product. Note the plus sign between the two reactants. Anytime you have more than one reactant or more than one product, you have a plus sign between them. So if I were to ask you on a quiz or a test which of the following is not a reactant, you're going to look over here on this side, the product side, and you're going to choose H2O. If I ask you in a multiple choice question, how many reactants does this equation have? You're going to look on the reactant side. You'll see the plus sign there, so you'll say it has 2 reactants. I do ask questions about reactants and products and the general formatting of an equation on a pretty regular basis. You need to know what exothermic and endothermic reactions are. Exothermics are the ones that warm things up, like those little instant hand warmers that you buy at Walmart. In an exothermic reaction, we have an extra amount of energy, or energy exits the reaction. We start off with high energy reactants, substances that store a lot of energy in their chemical bonds. When the reaction occurs, we break those bonds and we release that energy. Some of that energy is absorbed by our products. Some of that energy is used to make, in this case, the water and the carbon dioxide. Methane is natural gas. You know when you burn natural gas, you release a lot of energy from it. This is the substance that is predominantly used in gas water heaters, in gas furnaces, in gas stoves. When we burn this, we're breaking chemical bonds and we're releasing a tremendous amount of energy. Some of that energy goes into making the water and the carbon dioxide, but not all of it. These are low energy products. They cannot absorb all the energy that the methane releases. So that extra energy, the one that's not absorbed, is released as heat. Goes off into the environment, raises the temperature of the environment. We use it to heat our water, we use it to cook our food, we use it to heat our homes. That's the exothermic reaction. Again, high energy reactants, low energy products. There's extra energy. The energy exits the reaction in the form of heat, warming up our environment. The opposite of exothermic, endothermic. The endothermic reaction, we have the opposite scenario. We have low energy reactants. We have a substance like water, which is a relatively low energy molecule. That's why water is so stable. That's why there's so much of it on Earth. That's why it's been around for so long. That's why the water you drink is millions of years old. It's a very low energy substance that makes it a very stable substance. If we want to break the bonds in water and produce hydrogen and oxygen gas, we're not going to have enough energy in these water molecules to do that. We're going to have energy from our environment. We're going to have some extra energy added to it this time. When we break the bonds in the water, our products will absorb every bit of that energy. But it won't be enough. There'll be a shortage. So we're going to have to give it some energy. We're going to have this energy enter our reaction to give us the rest of the energy we need to form our high energy products, our hydrogen and our oxygen. Endothermic reactions typically cool down the environment. When we take this energy and we put it into our products, when we let this energy enter our reaction, this energy is coming from the surroundings. It is taking the energy away from its container. In most cases, that is heat energy. In most cases, that would cool down the environment. This is like those instant cold packs that athletes use. You break the little glass tube inside and the two chemicals mix. They're trying to make high energy products. They don't have enough energy on their own, so they get some energy to use as a reactant from you. They absorb that energy from your body, making your body cool down. In the case of this reaction, we wouldn't see a temperature change in order to make it happen. We'd actually have to run an electrical current through it. And the electrical current provides the energy that we need to make these new high energy products. If there is no current, it's like taking this reactant away, and the reaction just doesn't happen. But when that electric current flows, it pumps enough energy in to make these two unstable products, these two high energy products. Totally opposite, totally different way of reacting. We need to know the indicators of chemical change. We need to know what we can look for that tells us that a chemical change has occurred. We can't see atoms and molecules breaking apart and recombining together. So we look for a few things, and these are four of the most common indicators of chemical change. Bubbling is one of them. We're talking about spontaneous bubbling here. We're not talking about putting a straw in it and blowing. That is no way, shape, or form an indicator of chemical change. But what we're talking about here is forming bubbles on its own. A piece of chalk and some kind of acid like hydrochloric acid. We mix these two things together, it starts to foam up like vinegar or baking soda does. It's making bubbles on its own. That is a good indicator of chemical change. Changes in temperature, and again we're talking about spontaneous changes in temperature. We're not talking about throwing it in the microwave and heating it up. We're talking about taking two chemicals that are at 25 degrees Celsius, mixing them together, and all of a sudden the temperature goes up. In this case it shows the temperature going up to 30 degrees Celsius. We didn't put it in a microwave to heat it up, all we did was mix these two things together. It's heating up on its own. That is a spontaneous change in temperature. It's an exothermic reaction that we're looking at here. If the temperature goes up all by itself, you know you've got an exothermic reaction. If the temperature goes down all by itself, you know you have an endothermic reaction. So look for spontaneous changes in temperature. Changes in state, other than bubbling, obviously when things bubble we're making a gas. We can also make solids. It's called a precipitation reaction. You're making what's called a precipitate. We mix these two things together, this black strip of metal, probably magnesium or something like that, and this acid. Mix them together, we get this white solid that's forming. It wasn't there before. We're making some new solid here. This is called a precipitate. Making a solid spontaneously. We're not sticking this in the freezer to make a solid. We're just mixing these two things together and there, poof, there's a solid. Spontaneous. It's magic. That is an indicator of a chemical change. And finally, a spontaneous change in color. And again, we're not talking about putting food coloring in it. That's not a chemical change at all. That's just making a mixture. Here we have this wire, this metal wire, a copper wire. We have this clear solution. Mix the two together and it turns blue. Again, by itself. This new blue color, this new white solid, these bubbles, those are new substances. Those are something that we did not have before. Those are chemical changes, and chemical changes are chemical reactions. So we look for these common indicators. Whenever you see them happening spontaneously, you know that a chemical change is taking place. Finally, you need to know a little something about reaction rates. Reaction rate is simply how fast the reaction takes place, and you need to know how to speed it up or slow it down. We can change temperature to do that. The collision theory tells us for particles to react, they have to collide with each other. If we want to speed up the reaction, we have to collide harder, and we have to collide more often. Increasing temperature will do that. Recall, increasing temperature makes the particles move faster. If they're moving faster, they hit each other harder, they hit each other more often, it's going to react faster. We can change the particle size. If we want to speed the reaction up, we make the particles smaller. This gives us greater surface area. This gives us more targets for collisions. Smaller particles, more targets, more collisions, faster reactions. If we want to slow it down, we make the particles larger. By making the particles larger, we have less surface area. We have fewer targets. We have fewer collisions. We have a slower reaction. We can change the concentration. If we want to speed a reaction up, we have to use highly concentrated reactants. That's not the same amount. That's not the same as high amount. We have to use high concentration. That means we take the particles we have and put them in a small space. In that smaller, more confined space, they will bump into each other more often. They will react more often. If we want to slow it down, we lower the concentration. That means we put them in a bigger container. We spread them out. And the more spread out they are, the slower they will react. And finally, we can add a catalyst or an inhibitor. These work a little differently. Catalysts will speed up the chemical reactions. Inhibitors will slow them down. What the catalyst does is basically get our reactants and force them together. It lowers what we call the activation energy. It reduces how hard they have to hit each other before they react. So that will speed up the reaction. The inhibitor does the opposite. It gets in the way. And since it gets in the way, it slows our reaction down. As is always the case, if you have any questions, make sure that you post it to the wall or ask me sometime in class. That's it for chemical equations.